Thanks for coming. So today we have Chien-Chung Huang from Paris, and we'll talk about matroid intersections, sparsification.
Okay, everyone, welcome. So this is my joint work with François Sellier, who is my PhD student. So this talk I'm going to shift between the graph matching and the matroid intersection. So let's start with the graph matching. Everyone knows the problem. I have a bipartite graph or general graph. I want the matching. Okay, and there is something which is very, very in the mode. Is the skeleton. So for some reason, I want to have a smaller graph, but I want this smaller graph to still have a large matching. And the motivation of such a sparsifier should be very easy to find. We are talking about big data all the time. Okay, so it would be better if I can throw away a lot of edges so that the remaining graph still has a large matching. Okay, and then the application, as I mentioned, we are talking about big data. So in fact, in other computation models, such as sparsifiers are very, very useful. In a dynamic setting, in the communication complexity setting, and in streaming. I will talk about some of them in the next few slides. Okay, and then now let's go to the matroid. I don't know how many of you are familiar with the matroid. Okay, but anyway, here's the definition. So I have a matroid. V is the ground set, and I is the family of the subset of V. And then if you satisfy the three conditions, then you have you have a matroid. The empty set is independence. Okay, this I is called the independent set. Okay, empty set is independent set. And suppose X is a subset of Y and Y is independent, then X has to be independent as well. So it's like a downward close. Okay, the third property is the most interesting thing. Suppose you have two independent sets, Y and X, and Y is bigger than X, then you should be able to find element from Y added to X while keeping the independence of X. So that's the most interesting property of matroid. Okay, and all these are very standard terminology in the matroid literature. What's going on? Okay, so I is the independent set, and you have the rank. A rank of a subset of X is defined as the size of largest independent set. Okay. And you can also define the rank of the entire matroid. Okay, the first thing is important. I'm going to use a lot this notion of span. Okay, this comes from the linear algebra, if you are familiar with, if you still remember that. So the idea is that you can, for every set X, you can define a span, which is defined as all the elements that you can add into X without increasing the rank. Okay. So going back to our undergraduate linear algebra. This corresponds to all the vectors that are spanned by your set of vector X. Okay, so a little bit of background. So these things are invented or discovered in the 1930s, and in fact it's very interesting because it came up independently in several different areas. So that's a good sign. This is something very natural. And also they have nice applications. We are doing computer science, we care about applications. Okay, and the godfather of computer science in this area is Edmonds. Okay. Okay, so these are some very well-known examples in computer science in terms of the special case of matroid. So the first one is kind of the easiest one. It's uniform matroid. So if you have at the most k elements, that's independent, otherwise not. A partition matroid is a little bit generalization. So you can imagine the ground set that have different colors. And if you take at the most k1 black element, at most k2 red element, and so on, then it's independent. Okay, but if you take more than K1 black element, that's not independent. So, okay, the third one is also very well known. It's graphic matroid. So I give you a graph. All the forests are independent sets. But if any set has a cycle inside, then it's not independent. Okay, the fourth one is the most general case, which is we call the linear matroid. I give you a matrix. Okay, and you can imagine the column to be the ground set. Okay, a subset of columns are independent, if and only if they are linear dependent. Okay, and it's well known that the linear matroid include these three cases, the special cases. Okay, now let's go talk about the matroid intersection. I just talked about one matroid, but now I can talk about two matroid. I have two matroid with the same ground set, I, V. Okay, here I want to find the largest common independent set. Okay, which is like this. Okay, so this is the very textbook material. We want to find the matroid intersection, the largest common independent set. And this problem could be solved in polynomial time. Okay, so I take a long detour to talk about matroid. Why is that? Because it's well known that bipartite graph matching is a special case of the matroid intersection. Okay. In case you are not familiar with, let me explain. So you can imagine that I define a matroid on the left and a matroid on the right. Okay. The edges are the ground sets. Okay, and on the left, I set that on every vertex, I take at the most one certain edges. Okay, if you satisfy this condition, you are independent on the left. And you define the same matroid on the right hand side. Okay, then a matching is independent in both matroids. Okay, so in this sense, a bipartite matching is a very, very simple special case of matroid intersection. Okay. So that's the motivation. Because bipartite graph matching, we know we can find the maximum quadratic matching polynomial time. So that motivates the question whether I could do the same thing about matroid intersection. And the answer is yes, as shown by Jack Edmonds. Okay. So now let me talk about the sparsifier. I give you a graph G, and then suppose H is a subgraph of G. And then I have two parameters, beta and beta minus. The condition is that beta minus has to be strictly smaller than beta. Okay, you can imagine these beta and beta minus are just integers. Okay, and then I claim that this H is the EDCS, H degree constraint subgraph, if you satisfy these two conditions. So that means in this subgraph H, if I have some edges, then the degree sum of the two edges of the two endpoints should be at the most beta. On the other hand, if some edge is thrown away, it's not part of the sparsifier, I require that the two endpoints, the sum of their degree should be at least beta minus. Okay.
When you delete H, do you delete H set of H or vertex set of H? In G delete H, what is the meaning of the notation?
It means some edge. Yeah, this notation is not very precise. It means some edge is part of G but not part of H.
So in the sense you're deleting edge set of H.
Yes.
Okay.
Yeah. So H is derived from deleting edges.
Okay.
It's not induced subgraph. It's just subgraph.
Okay.
So what's going on with this property? Here let me give you some intuition. This first condition essentially says that I don't want this graph to be too dense. I want this H to have degree at the most beta. Okay. So if I choose a small enough beta, that means that the size of H is not too big. Okay. So that's the first thing. How about the second thing? The second property essentially says that because I want the purpose of H is to keep the size of the matching big. Okay, so if I decide to throw away some edges, if some edge is part of G but not part of H, I should guarantee that I have enough substitute. And this is guaranteed by the property that in the graph H, the two endpoints still have a lot of neighbors. So even if I am part of the optimal matrix, I'm thrown away. That's okay, because I know that my endpoints still have a lot of possible neighbors. Okay, so they can be matched to someone else to replace me. So that's a little bit the intuition of this EDCS. Okay, so that's the big theorem. So this is something shown in the paper of 2025 in SODA. They show that if beta and the beta minus are roughly in the order of 1 over epsilon, then this H always gives you a 1.5 plus epsilon approximation. I mean, you can also think of this 2/3 approximation. Okay, and the important properties, as I said, that the first property says that the degree is at the most beta for any vertex. So that means that the entire sparsifier edge the number of the edges should be roughly V over epsilon.
Shouldn't there be conditions on which beta and beta minus is existing?
Yeah, I said beta minus are in this order. 1 over epsilon.
No, but for the first part, you said it always exists.
Yes. Okay, the existence is guaranteed when beta is okay. The sorry. So there is an existence result which says that if you satisfy these two conditions, then such a sparsifier always exists. Yeah, I didn't state it clearly. Yeah, but then because my beta and beta minus are chosen to be the order of 1 over epsilon, so it always exists. Yeah, but that's a good question. I mean, I claim there's such a nice sparsifier, but if it doesn't exist, that doesn't mean anything. Okay, so the answer is yes, there is always such a sparsifier. You can find in polynomial time, and it gives you a nice approximation ratio. Okay, so I just show you the relationship between the bipartite graph matching and the matroid intersection. It should be very natural for me to try to imitate the same thing for matroid intersection. I would hope to have a sparsifier for the matroid intersection. Okay, but then here is the first big question. What is vertex degree in the matroid context? It shouldn't be clear. It shouldn't be obvious. If it is the first time you look at this. Okay. Because in the case of the graph, you can somehow find a partition of the ground set based on their incident verses. But this is not the case for the matroid intersection. So you don't know how to somehow partition the ground set. It's unclear how to do it. Okay, I should mention that even the tiny generalization of bipartite graph matching is people don't know how to give such sparsifier. For instance, this is called the laminar matroid. I'm still looking for bipartite matching, but I add the restriction. I said on the left-hand side, at the most 2 verses can be matched, and the same thing on the right. So this is still bipartite graph matching, but I have now a laminar constraint. Okay, so this is a very slight generalization of the graph matching, because now I have the intersection of 2 laminar matroid. Okay, but even such a tiny generalization is unknown how to do it. It was unknown before our paper came out. Okay, so now I have to ask you to bear with me because I'm going to introduce a lot of definitions. Okay, but I think it's a good point just to let people ask questions if anything's unclear. Yes?
will it already be a spoiler if I ask you if the laminar bipartite matching is polynomial time or NP time?
It's a special case of the matrix intersection. And matrix intersection is in polynomial time.
Because it made me wonder, like, correct me if I'm wrong, but the analog question for vertex cover, if I give you a bipartite graph and vertex cover in bipartite graph is also polynomial time, but
Yes.
if I say that, if I give you budgets, if I say that the vertex cover should pick k1 vertices from one bipartite graph and k2 from the other, I think that becomes NP part.
I
So
don't-
is it similar?
I don't remember. Okay, but the budget constraint is like a knapsack constraint, so it's not a special case of matrix intersection.
So this laminarity thing saying that
Laminarity, because it's unweighted, but if you are talking about the budget, you have budgets on the verses. That kind of constraint is knapsack constraint, and that constraint cannot be captured by Matroid.
it's not a constraint on the vertices but on the sets. Like there are two sets, I only give you two integers, k1, k2, and I say that your vertex cover picks k1 vertices from the first part of the bipartition and k2 in the other. So the like.
But the goal is vertex cover.
Yes.
But no, that's not the matrix intersection problem. It's not surprising. I mean, otherwise I solve your NPR problem. Okay, good. So here's the definition. Yeah, as I said, that because it's unclear how to define the vertex degree, so now I have to introduce a lot of technical terms. Bear with me. So first thing is the notion of density. Give a subset U, I define the density as the size of U against its rank. Okay, and then if the empty set, the density is 0, and it's a non-empty set of rank 0, the density is infinity. Okay, and then I have to introduce the notion of Matroid minor. So there are two ways. The first way is called the restriction. So if you have V as the ground set, and V prime is a subset, you can define a new matroid M prime, which is M restricted to V prime. So in this context, the ground set is V prime, but the new family, new family of independent set is defined as this. It just means that originally it was independent in the entire family. Okay, the second thing is a little bit trickier. It's called a contraction. Given the matroid, I can also define a contraction. So U is a subset of V, and then you can define the contraction as follows. The ground set is V minus U. Okay, but the independent set is defined based on this definition. So U is a base. I mean, U is a subset, and then you choose any base. Okay, the condition is that if you want to be independent in the new matroid, it has to be the case that this S and this base together is independent in the original matroid. Okay, and then it is well known that the choice of the base, because if I say I have a ground set U, I mean a subset U, you could have many bases. And I'm saying that whatever base BU you choose, that always define the main matroid, the same matroid. Okay. Well, I suppose here many people are doing graph theory. Just think about graph. Just think of the contraction as the graph contraction. I will give you a concrete example. For instance, think about this. Okay, originally, these two edges is independent. Okay, I'm talking about the graphic matroid. And suppose now I decide to contract these three guys. So these are the U. Okay, and then what's the definition? The definition there is that to say that the question is how are these two edges still independent? the answer is no. Because out of the three, you can define a base. Either this guy or these two guys or these two guys. But then you can see this, there's a cycle. This, there's also a cycle. Okay. So it doesn't matter which base you are choosing. Because this notion in the case of graphic matroids, the same as just you contract the graph. Okay. Okay. So now I'm going to introduce something called density-based decomposition. So imagine V prime. V prime is gonna be my sparsifier. I'm going to define a new matroid, N prime, based on this sparsifier. And then I'm going to define a density-based decomposition as follows. So imagine K is the rank of the original matroid. What I'm going to do is I'm going to do a greedy algorithm, apply on this V prime set. Okay, so what I'm going to do, U1, in the beginning, U1 is the largest, densest subset. Okay, and after you have U1, you do a contraction. You define U2 as the largest, densest subset in this contracted matroid. And you do this in a recursive way. Okay, you do this k times.
So what do you mean by largest densest? Like
because the densest subset, there could be many densest. Okay.
Among all
Yes.
densest subset of same density, you choose the largest one.
Yes. And also the densest subset, in fact, is closed under intersection and union. So there's a unique largest independent set. And you can find in polynomial time. Okay. I will be honest, when we wrote that paper, we didn't know how to do this. And then some reviewer told us this could be found by some marginal function minimizations. yeah. At that time, we didn't know. Okay, let's run a concrete example. Imagine that this is the llama matroid. So imagine this is, so I hope everyone here knows the definition of llama matroid. You have the tree structure, and on the internal leaf, you have the constraint, saying that how many elements you can take from the subtree. How many leaves? So here it means that from out of V1 to V10, you can take at most 2 guys. And here you can take at the most 3, and so on. Okay. So let's apply my greedy. And okay, the first U1 that I find is gonna be this one. Why is that? Because I choose 10 guys, and the density, the rank is 2. Why this laser doesn't work at all? No, he told me that I used the first button.
Yeah, that's right.
Oh yes, okay. So okay, good. This part has density 5. Because you have 10 guys against the rank 2. So the density is 5. But this part, you have density 14 divided by 3. So that's less than 5. Okay, and then if the entire tree, that's gonna be 17 divided by 4. Okay, so the first one, the U1 is gonna be this part. I have density 5. Okay, so U1 is this. Okay, and then remember, after I find the first U1, I have to do a contraction. This contraction in this context means that, okay, let's go back to the previous slide. So if this is the entire tree, I contract this part. That means that right now, you can only take at the most 1 more guy. Okay, so that means that in the second step, this part will have density 1, density 4. You have 4 against 1. Okay, but here you have only 2 and so on. Okay. So that's why we get this. U2 is gonna be this. Density is gonna be 4 against 1 against, you get 4. And U3 is gonna be you take all the 3 guys remaining. Okay. And the U4 is empty. Okay. And you probably noticed that the densities that I found are monotonically decreasing. It's not surprising. Okay. Bear with me. Just one more definition, then I will show you the good stuff. Okay. So V prime is my sparsifier. Okay, and then I just show you a decomposition from U1 to UK. And now I can define an associated density for everyone. So I should make sure this. This associated density is defined over all the elements. Okay, and what is the definition? I look at any element V. I choose the first UI such that the union from U1 to UI together span this element. Okay, then the density is gonna be the density of UI. Like this. Like this. J is the smallest index so that V is spanned by the union from U1 to Uj. Okay. Yes?
You have V and V prime in your definition. Is it that you are only taking a decomposition of a subset of V?
I don't understand.
No, why do you have two sets, V and V prime?
Because V prime is the sparsifier. I use the sparsifier V prime to define the decomposition. But now I'm going to associate the density with for everyone, not only for the people in V prime.
Okay.
Yeah.
So when you define density based the decomposition, you start with some.
This is V
prime.
I have V prime. Okay, for the moment, don't forget how I find this. Just imagine I found it. Okay, and then I'm going to do a decomposition from U1, U2 to UK. Okay, and now the associated density is defined for everyone else.
Okay.
So for this guy, his density is gonna be the first. Suppose U1 doesn't span him, the union doesn't. But suppose U3 together, the three guys together span him. Then the density of this guy is gonna be the density of this U3. Okay, and notice that by this definition, what is the every element here? What's the density? Suppose this is U4. Then the density of this guy must be the density of U4. Because remember, U1, U2, U3 together cannot span him. Because I'm doing a greedy. If originally these three guys can span this guy, then this guy should have been added into U1, U2, U3. Because I want to increase my density. Okay, so I want to because someone is in part of my span, I want to increase my density. I should take everything in my span into my set. Okay, so essentially this definition says that every element here has the same density as this group, this group, this group, and so on. Okay, and for the people outside, I also have a density. Okay, and which is based on which component guaranteeing that U1 up to UI span this guy. Okay, so that's the associated density. Okay, it's a very long introduction. Yeah, I already spent 30 minutes. Let's see a concrete example. So remember, this is a bipartite graph we started. So imagine that the solid lines are my sparsifier. Okay, and then the dotted line are those that are not part of my sparsifier. Okay, just imagine these guys are the U1, U2, U3 I'm talking about. Okay, let's do the greedy decomposition. In this case, it's very simple because this guy has degree 4. You have four edges against the rank of 1. So this density is 4, this density 2, and this is 1. So this is gonna be my U1. Okay, and then in this context, the contraction is meaningless. Because this is the definition of the partition matroid. Even if you contract this part, that doesn't change anything about the density of these people. Okay, so now look at this guy. This E0, this is part of the U1, so his density is 4. How about this guy? This guy E1 is not part of the sparsifier V prime. Okay, so I'm looking for the first time the union of U1, U2 up to UI, the first time I can span this guy. But in this case, this U1 doesn't span this, but together they will span this guy. Okay, so E1 has density 2. And how about E2? This guy is never spanned by any, even if you take the union of U1, U2, U3, they don't span him. In this case, the density is 0. Okay. Okay. After such a long introduction, I can introduce my sparsifier. So if you gave me two matroid M1 and M2, if you get two integers, beta and beta minus, yeah, the beta should be 7 bigger than beta minus. And then a subset of V prime, I call this a beta beta minus DCS. DCS means degree density constraint subset if you satisfy these two conditions. Okay. So remember, every element I can define associated density with M1 and with M2 separately. Yeah, just think about this. Just imagine this is M. I1, you have M1, you M2, and then here you have the same thing, V and the V prime. Of course, here you might have a totally different decompositions. Okay. Then look at any element. Maybe this guy is in here and here. So here he will have an associated density. Here he would have a different associated density. Okay, but I put the constraint that their sum together is beta, at the most beta. And if some element is not there, yeah, sorry, I should say it more clearly. If someone is in here, then the associated density of him together should be at the most beta. If someone is here, then the sum of associated density should be at least beta minus. Okay, and then if you are familiar with Matroid in the metric literature, you should be able to see that this definition is exactly equivalent to EDCS if the two matroids are just two partition matroids. It's not immediately obvious if this is the first time, but believe me, if the two M1 and M2 are just partition matroids, this definition reduces to the EDCS. Okay. Okay. And then, similarly, I have to promise you that such a sparsifier exists, otherwise it's pointless. I mean, I cannot promise you something which is so wonderful, but it doesn't exist. That doesn't make any sense. Okay, so here we show that, yes, you can always find such a sparsifier, and you can found in polynomial time. That's important for us. We are doing computer science. Okay, so that's the first thing. This is existence. And the second thing is that we promise you also the approximation ratio. Okay, so if you satisfy this condition, beta is at least 7 bigger than beta minus, and you satisfy this constraint, then you always have a 1.5 plus epsilon approximation in terms of matrix intersection. Okay, let me give you some concrete applications.
So can you go back to
Yes, of course.
Is it already interesting that in the graph case, the difference between beta and beta prime was supposed to be at least 1?
Yeah,
But
in fact, some people ask me this question. In fact,
I mean, my question more is that even though your gap is larger, I don't see the difference in the final approximation guarantee. And is that really surprising or?
No, this should be big O of epsilon, so I'm hiding some constant.
So like the 7 thing will depend, that plus 7 thing, it's sort of implicitly dependent on the plus epsilon?
Yes.
Okay.
So here V prime is, I mean, of course, given as an output, right? So you cannot fix you are not fixing V prime, but V prime is.
We have an algorithm. If you have given me V, we have an algorithm to give you the V prime. And this V prime is the sparsifier, and guaranteeing this theorem.
So the V prime is the union of all these U1, U2.
Yes. It should be the other way around. The V prime is given to you, and then, yeah, okay, that include. Yeah, this V prime is the union of U1, U2. Yeah, but then remember, you have 2 different matroids. So the U1, U2 to UK could be different in the 2 different matroids.
Oh.
So is the bound 3/2 is tight?
Yes. Asymptotically.
Yeah.
The
So
epsilon, there is
cannot-
an epsilon term. There is some small constant hidden in the epsilon expression.
But you cannot improve to say 5/4 or something like that.
No.
Okay. Right, I see.
There are some lower bound results showing that you cannot do it. Okay, so let me give you the first application, compression complexity. Okay, again, go back to the Matroid, the graph matchings. Imagine I have a graph, and I give a subset of edges to Alice, the other subset to Bob. And now the question is that how many edges Alice has to send to Bob, so that Bob can still get a large matching in the entire graph. So this is just using the language of Matroid graph matching. But here I'm asking the same thing. Suppose the ground set is separated into VA and VB. Okay, and then Alice wants to send the small subset VA prime, so that Bob can still get the large Matroid intersection. Okay, so this is, of course, there's a trivial answer. Alice just send everything to Bob. Then, of course, Bob can recover the original optimal solution. Yeah, but that's pointless. The entire point is that I want this V prime A to be as small as possible, while guaranteeing that Bob still get the large matching or large Matroid intersection.
What do you mean by matrix intersection here? So VA, VB are disjoint sets, or
Disjoint.
and then you have a matrix on VA and matrix. What is matrix? Matrix on the union.
No, so
I agree with you.
Union
you have 2 Matroid.
Uh-huh.
Okay, but now I assume this V is separated into VA and VB.
This is the ground set is the union of VA and VB.
Yes. And then Alice has to send the subset to Bob.
Mm-hmm.
Okay, so that VB and the VA prime together, you still can get the large Matroid intersection.
But,
Yes?
but Bob, for example, does he know all the independent sets in I2?
Good question. No, Bob. No, don't be confused. Both of them have 2 Matroid. Okay, but we assume there's an oracle, so that Alice and Bob can query this oracle whether a subset is independent in here or in here. So that's the assumption. Okay. So this problem has been studied in the context of bipartite graph matching. And then it is known that there's a protocol. So Alice sent a message of this size. So it's like roughly linear. And then Bob can build a matching of 1.5 plus epsilon approximation. Okay, and then it is known that, so this somehow addressed your question before. So if you want to do strictly better than this, like 5/4, it's impossible. I mean, in the sense of Alice had to send the message much bigger. It has to be super linear. Is that okay? So that's one. So what's the main theorem? So essentially we show the same thing. We show the same thing. It's possible that Alice send a message of this size. This mu of v means the size of the optimal solution. So it's roughly like in terms of, if you are talking about graph matching, so it's like the number of verses. And then we can still get 2/3 approximation. Okay. So this means that at least in the case of one-way communication complexity, there is no difference between the matching and the matroid intersection. Okay, the second application is the streaming model. So here's the setting. I give you element one by one. Okay. But you have very small, yeah, I'm very old-fashioned guy. I'm still using the soft disk. Okay. Okay, so you have this very small disk and give you so much data. Okay, so you cannot store everything. So the question is that at some point you have to throw away some element. But if you throw away that element is gone forever. Okay, so the question is that when all the stream stops, I still want you to tell me a large matching or a large matroid intersection. Okay, this is a setting which is a little bit simpler. So in the adversary model, I'm talking about the online setting. The adversary can choose the element. He can observe your behavior and then choose the element, design the element the way he wants. But here is a weaker model. The random order model means that the adversary chooses the elements. Okay, but he can only do a permutation. And then these elements are given he can choose, he can design all the elements beforehand. But then in the beginning there will be a random permutation of all the elements. And these elements are given to you one by one. So in this random order model, his power is much less. He chooses the element, but he cannot control the permutation. And he also cannot observe your behavior. Okay. Okay. Anyway, so this problem has been studied in the case of graph matching. And then it is known that you can do like, again, 1.5 plus epsilon approximation, plus or minus, using roughly linear space. And again, it is known that the random order model is really easier. Because if it's an adversary model, to do better than 1.693, you need superlinear space. Okay. So again, we managed to do the similar things. So again, you can imagine this u of v, mu of v is like n, so it's like roughly linear space, and we get 3/2 approximation. Okay, and then before our result, people can only do like 2 minus epsilon, 2 minus delta approximation. And then, again, this is the lower bound in the adversary model. So we show that there is also a difference between the adversary model and the random order model in the matroid intersection setting. Okay, so I have only 15 minutes left. I still want to tell you something interesting technically. Okay, so the first theorem says that we can guarantee the existence of the sparsifier, and we could find it in polynomial time. And the second thing is the big thing. We show that for such a sparsifier, there is always a good approximation, meaning 1.5 plus epsilon approximation. Okay, I have about 30 minutes. I still want to show you one theory. Because I think this theory is kind of cute. Even though this is not proof in our paper, it was in the previous paper. Okay. But our paper essentially is, our main theory is built on this proof. So I still think it's interesting to tell you how this proof works. And I think this proof is very cute. In fact, I think if you teach an algorithm class, you can teach it. So let's go back to the EDCS, the graph metric. I have a sparsifier. Okay. So remember, this H is the subgraph. Okay, and then I suppose here everyone here knows the definition of this Kernig's theorem. If I talk about the matrix, bipartite graph matrix, this is such a theorem which says that look at the largest matrix in H. Based on this matrix, you can create a decomposition of the vertices. Okay, and it is known that this A and the B is a vertex cover. Okay, and then there's no edges between A bar and B bar. You could have some edges from here to here in H, but there's no edges from here to here. Okay, so that's Kernig's theorem. Okay, so here's the first main claim. I claim that in the original graph, G, there should exist a matrix in A bar. Okay, sorry. There's a subset S in A bar and also a subset in B bar. They form a matrix in the origin graph G. Okay, and the size of this matrix should be exactly the difference of the largest matrix in G and the largest matrix in H.
Sorry, what was S?
S? I claim that there exists a subset S in A bar and also a subset S in the B bar, so that they form a matrix in the original graph G.
So I think we applied Koenig's theorem to which graph? Because
To H.
to the sparse thing.
Yes, this is sparsified graph. But now I'm talking about, this is, so in the sparsified graph, there is no edges from here to here. Okay, but I'm saying that if you look at the original graph G, what's going on? If I look at the original graph G, there should exist a matrix from A bar to B bar. Okay, and the size of this matrix between S should be exactly the difference between G and H in terms of the matrix size. It shouldn't be hard to prove. If someone has taken my course last year in summer school. Okay, it's well known that if right now your matrix, so you're starting with your matrix, the red one is the matrix in H. And if the G has larger matrix, it is known that the difference of the two matrices should correspond to a bunch of the augmenting paths. Okay, and these augmenting paths all started from A bar to B bar. Okay, so what does that mean? It means that you started with some, what's going on? You started with some vertex which is unmatched here. And then you go like this. At some point you have to go from A bar to B bar. Okay. And all these paths are disjoint. So every time if you cross from A bar to B bar, that edges will give me the matrix that I'm talking about here. Okay. So that's one thing. Okay, so now let's define H prime as a subgraph of H. Okay, and the subgraph is induced by all the edges of S. Yeah, here I should write there's an H here. The gamma of S is the neighbor of S in the sparsifier H. Okay. So H prime is the subgraph of H. Essentially, it corresponds to S here, and the neighbor here, and S here, the neighbor here. Okay, and then the first thing I want to claim is that the number of the edges should be this. Okay, I'm using the first property of the EDCS, if you remember. No, second property. Did you remember? So I said that, so if this edges is part of G but not in H, I said the degree sum of them should be at least beta minus. Okay, so this is, I just said there's a matching here. This is A bar, this is B bar. Okay, but this matching is part of G but not in H. So that means every one of them is a missing edges. So you apply the second condition. You apply the second condition to every single edges of them, then the degree sum of these people should be exactly 5 times beta minus. So that's how I got this expression. So I'm using the second property of the EDCS. Okay.
But H prime is a subgraph of H.
Yes.
So you're talking about the edges inside H, not in G minus H.
Yeah, but H prime is exactly defined based on the neighbor of these people.
I thought H prime was defined based on the neighbors of S in B, not in B bar. No? Like in the picture,
Yes?
H prime contains the neighbor of S, which is in A bar, and the neighbors are in B, not in B bar.
Yes?
But here you're looking at the edges.
No, so
between A
think
bar.
about this. This is B. Yeah, so I should write like this. So these are missing edges. So
Yeah.
every one of them have some neighbors. Okay, but then, so these edges are all come from H. But these people are all defined as part of the H prime.
Yes.
So that's what I mean. Sorry, I missed your question.
I mean, I don't see how do you say that the degree sum of two adjacent pairs is at least beta minus, and for that you need to take the degree sum of those adjacent pairs which are in
Yes.
G.
In H. The condition is that,
So what you say?
yeah, for every edges that is missing, the degree of H of U plus H of V is at least beta minus. Okay, and then by my construction, this is equivalent to degree H prime of U. This is degree H prime of V. And the reason is because here every neighbor, because this is the set S, all their neighbors are part of the H prime. So these two guys are equivalent. Okay, yeah. So now let's go to the second thing. Okay, so I just what I do is that I look at every edges here that are missing. And now this time, what I'm going to do is like this. I'm going to look at this guy. I look at these edges. I'm going to enumerate all his neighbors. Enumerate all the incident edges of this guy. I'm going to do the same thing for every vertex. Okay, and then what's the first condition? I say that if this edge is part of the edge, the degree sum of these two guys together should be at the most beta. Okay, so essentially that's what I'm going to do. So I'm going to do this for all the edges. So that means that's how I got this square term. The degree of H here, H and H prime is the same because I count all his neighbors in H. Okay, so this is how I got the square term. because I'm counting every incident edges this guy has. So I got this. And also for the gamma S. Okay. And then because of the convexity, I got this. Okay. And then you can move around the term, you get this expression. So this time I got the upper bound. I mean, I got the upper bound on the size of the H prime. Okay. So I think we can do a little bit red bar. Okay, so this is the second property I just used. I know I have a lower bound on the size of H prime, which is this. Okay, then remember I said S is exactly the difference between the optimal matching and the optimal matching in H. And can I have the second slide, which is I enumerate all the edges that are present in H prime. I got the upper bound of E of H prime, like this. Okay, and then this term, gamma of S, is gonna be at the most mu of H. Why is that? Because the gamma of S is a subset of A union B. And remember, A union B is the vertex cover, optimal vertex cover in H. And that's the upper bound on the size of the matrix mu of H. Okay. Anyway, I'm going to use these two facts to derive this. Okay, maybe I didn't explain it very well, but I think this proof is kind of cute. Okay, offline you read the paper, you will agree with me that this is a very nice proof. My explanation is not very good, but the proof is very good, believe me. Okay, so in this case, I choose beta and beta minus to be close enough. That's almost 1. So that's how I got 1.5 plus epsilon approximation. Okay. So what are the ingredients? So as I said, our paper is built on a much more sophisticated generalization of this proof. But the ingredient of the papers are, the proofs are here. What are the ingredients? I need a nice certificate to capture the optimal solution in the sparsifier. So that's the first thing. And the second thing that I want to find a subset S that can somehow capture the difference between the largest matching you have in H and the largest matching you have in the original G. And the third thing is what I'm using is just the property of the EDCS, and I'm doing counting argument. Okay. So the proof, in fact, is not so difficult. So if you don't follow me very well, it's my fault. It's not the fault of this paper. Okay, good. Okay. I think I'm running out of time. So our paper essentially is based on this basic idea, but then because we are talking about matrix intersection, so it's much more difficult. Yeah. So about the duality, we are using a theorem of Jack Edmonds. He says that there's a minimax theorem to capture the size of largest matrix. And then this minimizer will be our vertex cover. And yeah, I think this will become too technical. Yeah. And I'm going to do a greedy and so on. Okay, I think I will just skip to the last slides, which is this.
Thank you. Any questions?
Yes?
Can you do sparsifiers for matroid parity?
Good question. Of course, we tried and failed.
Wait, isn't matrix parity an instance of the
No, it's stronger.
stronger?
It includes matrix intersection and matching. Draft matching.
We try. It's tough. Even if you are talking about very simple matroid. Yeah, but I think it's interesting. But I know it's tough. Yes?
Is this sparsifier has any connection with some other type of sparsifier? For example, say spectral sparsifier or
As far as no, not really. Yeah, of course, depending on the application, there are different types of sparsifier. Yeah, but if you are just talking about the matrix intersection or graph matching, I don't see a clear connections. And also the term sparsifier in fact is not very standard. I mean, people sometimes call skeleton or sketch or spanner. I mean, that depends on the application. But then somehow they say the same thing. You just want to reduce the input or kernel. I'm talking to you. Yes. Or kernel. Essentially, you just want to have a small subset of input, and then you want to keep some nice properties. Yes.
So when you define density, I was curious why, I mean, normally for me, I would divide by rank plus 1 because
Why is it?
of the graphic nature that corresponds to the edge density. Because so you divide by rank, so I was wondering whether this was like particular.
No, in fact, the reason we define like this is because we want to imitate the partition matrix in the matching context. Because as I said that here, if you are talking about like this,
Yeah.
it's very natural to say that this guy has density 4, and then to say this guy has density 2. We don't want to say this is divided by yes 4. We don't want to say this is 4 divided by 1 plus 1. That's a little bit strange. Yeah. So the original motivation and the entire paper is closely linked to the fact that we are trying to imitate the behavior of the graph matrix.
Right. Any other questions?
So when you make this density decomposition, what if you do it in the backward order, like instead of decreasing density, like you try to bound the maximum density while you're contracting the sets. So does it make sense? Have you tried?
So you want to
So you want
define
to
the sparses.
Yes. You always contract the
Good
sparses
question.
one and try to bound it. I wonder, like, so for example, when you do this, I guess if you apply it to the graphing matrix, you can find the densest subgraph, right?
Not exactly, because it has to
Something
divide
like-
plus 1.
Yeah. Okay, something close to that.
Yes.
So I wonder, like, can you mimic like a bounded degeneracy, or I don't know.
Bounded degeneracy.
Yeah, bounded degeneracy, or like
Yeah,
you
remind
want to
me-
find a sparse.
remind me the
okay,
definition
let's
of
say
this.
sparse decomposition.
Could you first remind me the definition of degeneracy?
Sorry.
Remind me the definition of degeneracy.
Vertex. You order the vertices. So that's so the vertex is always have bounded number of neighbors. And it
Yes,
increases you.
Colin talked about this last time. In your talk, you talked about this.
Yeah.
Yes, I remember. I haven't thought about it. I don't know whether it could lead to something interesting. I don't know. I cannot answer this on the spot.
Any other questions? Good. Let's thank the speaker.
Okay.